Welcome back to Calc Lessons. Today we're going to go back to taking limits. It's been a while. We've been doing a lot of integration. We've been doing techniques of integration. So as you are working on your second exam, we're going to take a break from that for a little bit, and we're going to look at a new trick for computing limits. Back in Calc 1, we had some troubles with limits that looked like this. One of the big issues, if you look at the first limit that I put down, as x approaches 0, the top is going to 0 and the bottom is going to 0. And so this looks in essence like 0 over 0. I'm putting quotes because we're not allowed to divide by 0, but we have no idea what's going to happen because the top says it's going to 0 and the bottom says because you divide by 0 it's going to blow up. What happens? And the answer is anything could happen. It could go to something, it could go to 0, or it could blow up to infinity. And there's examples of all three of these things happening. So we need a different tool to help us decide what it actually converges to if the limit does exist. Same thing for the second one. When x goes to 1, you'll notice that the top becomes 1 plus 3 is 4. Minus 2, or square root of 4 is 2. 2 minus 2 is 0. So the top goes to 0. The bottom is 1 minus 1, which is also 0. So once again, this fraction looks like 0 over 0. This one here is a little bit different. As x approaches 0, the natural log of x goes to negative infinity, and 1 over x goes to infinity. So this one looks like negative infinity over infinity. And again, we don't know who's going to win. Is one infinity bigger than the other? Is it just going to crush? So is it going to blow up? Is it going to stabilize? Or is it going to blow down? All three could happen. We just don't know. And then the last one is a little bit similar, but instead of approaching a number here, we can actually ask the same question about if x goes to infinity. And here, as x approaches infinity, e to the x goes to infinity, x squared goes to infinity, and again, we don't know who's going to win. Is the top infinity somehow bigger than the bottom or not? So this one is just looks like infinity over infinity. All of these, we're going to learn a tool that can help us solve each one, and the tool is called L'Hopital's rule. The reason why you have this little hat over the O is the French language is weird. There was a particular king that decided that there were too many silent letters in the language. And so instead of keeping those letters like we have in English, they just threw them away. But every time a letter was thrown away, it was replaced by an accent. So this one, if you see, it looks very much like the English word hospital. What happened is in French, the S wasn't pronounced, so they dropped it, and they just put a hat instead. So this is pronounced L'Hopital. So this is L'Hopital's rule. And it says the following. Suppose that you're looking at the limit either as x approaches a or as x approaches an infinity of a pair of function f of x divided by g of x, which have the form that if you evaluate these limits, it either looks like 0 over 0 or some infinity over some infinity. So it's got to look like one of these. And that around the limit, both f and g are differentiable. Then you can find the limit either as you approach a or as you approach an infinity of f of x over g of x by instead looking at the limit of the ratios of the derivatives. Provided this exists. So if this limit exists, then this limit is going to be the same as this one. So basically, L'Hopital's rule says if you want to take a limit of a fraction of two functions, then you can do it by taking the limit of the fraction of the corresponding derivatives. This does not say that you use a quotient rule, not at all. You don't take a derivative of what you see. Instead, you do the derivative of the top divided by the derivative of the bottom and look at that limit. And if you get a number, that number is the same as the original limit. Very, very powerful. Now, there's a catch. You can only use it if your fraction looks like 0 over 0 or some infinity divided by some infinity. So these situations here are the ones we can solve this way. You cannot use it if it looks like 0 divided by infinity or any other form that you still don't know, okay? So you have to make it look like this first in order to use it. In the second video, I'll show you how to use this for expressions that don't at first look like you could use L'Hopital's rule. You end up using L'Hopital later as you do some algebraic tricks first to set it up. So let's go ahead and see how we use L'Hopital's rule to solve all four of these. You can find L'Hopital's rule written in all of its forms in the book, so I don't really care that you write down what it is. I want you to see that you know how to use it. So use the official theorem in the book to make sure you have all the pieces right. But let's go ahead and use it to solve these four limits. Let's start with the first one. Let's look at the limit as x goes to 0 of sine of x over x. Instead, we're going to compute the limit as x approaches 0 of the derivative of sine, which is cosine of x, over the derivative of x, which is just 1. Hey, well, that's not bad, because as x approaches 0, cosine of x is 1. So this limit is 1 over 1. So our original expression, by taking derivatives, we found the limit to be exactly 1. This is the great use of L'Hopital's rule. This is where it shines. You take an expression that you weren't sure, and you actually find the limit. Let's look at the second one. Limit as x goes to 1 of the square root of x plus 3 minus 2 over 1 minus x. Now, back in Calc 1, you actually were able to compute this limit, but you had to use a trick that multiplied top and bottom by the conjugate of this to get rid of the square roots and then hope for things to cancel and simplify. And that did, because the top ends up being factorable in some sense by 1 minus x. It was complicated. It was clumsy. It was hard. Let's use L'Hopital's rule to see how it works. Again, we have something of the form 0 over 0, so we're allowed to use it. We're going to still look as x approaches 1. This time, the derivative of the top. What's the derivative of square root? Oh, it's 1 over twice the square root. So 1 over 2 times the square root of x plus 3. And this is just fine because the derivative of negative 2 is 0. So this gives us the derivative of the top function. The derivative of the bottom is just negative 1. Well, look, now we're fine, because now we can actually plug in 1 and not have any issues here. I have 1 over 2, and we have root of 1 plus 3 is 4. So this is just going to be negative a quarter. So by taking a derivative, all of the places where we had zeros and divide by zeros just go away, and we actually find our limit to be negative a quarter. Notice that this was of the form 0 over 0. This is of the form 0 over 0. This 0, 0 converged to 1. This 0 over 0 converges to negative a quarter. This is what I mean by saying that if your form is of the form 0 over 0, you don't know what it's going to do. Anything is possible. So this is really, really powerful for handling a whole family of limits we could not do before. Let's move to the third one. This one's a little bit different because this is our first one that looks like an infinity over an infinity. So let's look at the limit as x approaches 0 from the right. And you have to approach 0 from the right because natural log is not defined for negative x's. So x being positive is necessary. All of these could be one-sided as well as two-sided. That's completely doable using L'Hopital's rule. So we're looking at the natural log of x over 1 over x. And the top one goes to negative infinity. The bottom one goes to infinity. So it's of the form some infinity divided by another infinity. We use L'Hopital's rule. We take the derivative of the natural log of x, which is 1 over x, and we divide by the derivative of 1 over x, which is negative 1 over x squared. And dividing by a fraction is multiplying by the reciprocal. So it's the same as multiplying by x squared. So this gives us the limit as x goes to 0 from the right of negative x squared over x, which simplifies down to x. Limit as x goes to 0 from the right of negative x. And now we're not dividing by 0, so we can just plug in 0, and we get actually that this goes to 0. So this is interesting. This is saying that 1 over x forces, it goes to infinity faster than the natural log of x. So this is, well, useful result. One more, last one here. We're looking at the limit this time as x approaches infinity of e to the x over x squared. Both of these functions go to infinity, and we want to see what happens when we take the limit. So limit x approaches infinity, e to the x over x squared. L'Hopital's rule says, yep, we can do this. It's infinity over infinity, so we take derivative of the top, stays the same. Derivative of the bottom is 2x. And we say, oh, shoot, this is still of the form infinity over infinity. Well, how about we use L'Hopital's rule a second time? Do it again. This becomes the limit as x goes to infinity. Derivative of e to the x is still e to the x. Derivative of 2x is 2. And now we're no longer in an indeterminate form because we have infinity over 2. This just goes to infinity. So because this one goes to infinity, it's going to force this one to go to infinity, and it's going to force this one to go to infinity. So this helps us actually decide a whole bunch of limits that we couldn't do before, and now we have a really good tool to do. The next video, like I said, we're going to see how to use this particular trick when it doesn't seem to be there to begin with. So I will see you in the next video.